So far we talked about the fully observable case, and I'd like to get back to the more general case of partial observability. Now, to warn you, I don't think it's worthwhile in this class to go into full depth about the type techniques that are being used for planning under uncertainty if the word is partially observable. But I'd like to give you a good flavor about what it really means to plan in information spaces that really reflect the type methods that are being brought to bear in planning under uncertainty. Like in my Stanford class, I don't go into details here either, because the details are much more subject to more specialized classes, but I hope you can enjoy the type flavor of materials that you're going to get to see in the next couple of minutes. So we now learned about fully observable environments and planning in stochastic environments with MDPs. I'd like to say a few words about partially observable environments, or POMDPs, which I won't go into any depth. The material is relatively complex. I'd like to give you a feeling for why this is important and what type of problems you can solve with this that you could never possibly solve with MDPs. So, for example, POMDPs address problems of optimal exploration versus exploitation, where some of the actions might be information gathering actions, whereas others might be goal-driven actions. That's not really possible in MDPs because the state space is fully observable, and therefore there's no notion of information gathering. I like to illustrate the problem using a very simple environment that looks as follows. Suppose you live in a world like this, and your agent starts over here. And there's two possible outcomes. You can exit the maze over here, where you get a plus 100, or you can exit the maze over here, where you receive a minus 100. Now, in a fully observable case and in a deterministic case, the optimal plan might look something like this. And whether or not it goes straight over here or not depends on little details, for example, whether the agent has momentum or not. But you'll find a single sequence of actions and states that might cut the corners as close as possible to reach the plus 100 as fast as possible. That's conventional planning. Let's contrast this with the case we just learned about, which is the fully observable case, but the stochastic case. We just learned that the best thing to compute is a policy that assigns to every possible state an optimal action, and simplified speaking, this might look as follows, where each of these arrows corresponds to a sample control policy, and those are defined in part of the state space that are even far away. So this would be an example of a control policy where all the arrows gradually point you over here. We just learned about this using MDPs and value iteration. The case I really want to get at is the case of partial observability, which we will eventually solve using a technique called POMDP. And in this case, I'm going to keep the location of the agent in the maze observable, but what I make unobservable is where exactly I receive plus 100 and where I receive minus 100. Instead, I'm going to put a sign over here that tells the agent where to expect plus 100 and where to expect minus 100. So the optimal policy would be to first move to the sign, read the sign, and then return and go to the corresponding exit for which the agent now knows where to receive plus 100. So for example, if this exit over here gives us plus 100, the sign will say left. If this exit over here gives us plus 100, the sign will say right. What makes this environment interesting is that if the agent knew which exit would have plus 100, it would go north from its starting position. It goes south exclusively to gather information. So the question becomes, can we devise a method for planning that understands that even though we wish to receive the plus 100 as the best exit, there's a detour necessary to gather information. So here's a solution that doesn't work. Obviously, the agent might be in two different worlds, and it doesn't know. It might be in the world where there's plus 100 on the left side, or it might be in the world where plus 100 on the right side, with minus 100 and the corresponding other exit. What doesn't work is you can't solve the problem for both of these cases and then put these solutions together, for example, by averaging. And the reason why this doesn't work is this agent, after averaging, would go north. It would never have the idea that it's worthwhile to go south, read the sign, and then return to the optimal exit. When it arrives finally at the intersection over here, it doesn't really know what to do. So here's the situation that does work, and it's related to information space or belief space. In information space or belief space representation, You do planning not in the set of physical world states, but in what you might know about those states. And if you're really honest, you find out that there's a multitude of belief states. Here's the initial one, where you just don't know where to receive 100. Now, if you move around and either reach one of these exits or the sign, you will suddenly know where to receive 100. And that makes your belief space, your belief state change. And that makes your belief state change. So, for example, if you find out that 100 is left, then your belief state will look like this, where the ambiguity is now resolved. Now, how would you jump from this state space to this state space? The answer is, when you read the sign, there's a 50% chance that the location over here will result in a transition to the location over here. 50% because there's a 50% chance that the plus 100 is on the left. There's also a 50% chance that the plus 100 is on the right. So the transition over here is stochastic, and with 50% chance, it'll result in a transition over here. If you now do the MDP trick in this new belief space, and you pour water in here that kind of flows to here and creates all these gradients as we had before, you do the same over here, and all these gradients are being created that point to this exit on the left side. Then eventually this water will flow through here and create gradients like this, and then flow back through here, where it creates gradients like this. So the value function is plus 100 over here, plus 100 over here, will gradually decrease down here, and then gradually further decrease over here, and even further decrease over there. So we get arrows like these. And that shows you that in this new belief space, you can find a solution. In fact, you can use value iteration, MDP style value iteration in this new space to find a solution to this really complicated, partially observable planning process. And the solution, just to reiterate, will suggest go south first, read the sign, expose yourself to the random transition to the left or right world, in which you're now able to reach the plus 100 with absolute confidence. So now you've learned pretty much all there is to know about planning under uncertainty. We talked about Markov decision processes, we explained the concept of information spaces, and what's better, you can actually apply it. You can apply it to a huge number of problems where the outcome of states are uncertain. There is a huge literature on robot motion planning. Here's some examples of robots moving through unknown environments that use MDP-style planning techniques. And these methods have become vastly popular in artificial intelligence. So I'm really glad you now understand the basics of those and you can apply them yourself.